Hello, my name is Richard Lobienko from Scottish Carbon Capture and Storage at the University of Edinburgh, and I'm very happy to welcome you to today's webinar. This is the project's fourth webinar, and today's topic is the framework for selection of prospective CCUS value chains and developing projects of common interest. We have two speakers for you today. We've got Kasbulat Shoganov from the Tallinn University of Technology, presenting the framework for selection of the prospective CCUS value chains, and Leandro Enrique Sosa from Ramble on developing of project of common interest. So I'd like now to hand over to our first speaker, Kasbulat. The floor is yours.
Hello, everyone. Can you hear me?
Yep.
My name is Kasbulat Shoganov. I'm a researcher at Tallinn University of Technology, Estonia, and CEO at Shoganergy Consulting. I will present today the results of work package 3 of the Horizon Europe CCUS Blend project, a framework for the selection of promising CCUS value chains in the Baltic and Mediterranean regions. I would like to thank all co-authors of this study for their productive cooperation from BRGM France, Ramble, Denmark, Polish Geological Institute, Sintef Norway, METO Turkey, Prospective Climate Research Germany, Utrecht University Netherlands, IOM Law from Norway, JOS Denmark, and Accelera from France. I will not focus on the summary too much. I will only mention that the objective of the study is to propose a framework for the selection of national and cross-border CCUS value chains and to apply it to 8 case studies in the Baltic and Mediterranean regions studied by Horizon Europe CCUS project. Here we reported the qualitative results of analysis and the framework for the quantitative SWOT analysis, which will be performed as the next step of the study using statistical multivariate analysis. Today, CCUS projects around the world inject about 50 million tons of CO2 annually. To achieve climate neutrality, we must increase CO2 storage from millions to billions of tons per year. One effective way to accelerate the necessary scale-up is by implementing CCUS clusters and hubs. The application of CCUS clusters and hubs offers many advantages: faster scaling, lower unit costs, reduced investments and cross-chain risks, governmental support, the creation of new jobs, potential revenues from CO2 utilization, synergies with renewable energy sources and CO2 negative technologies, increased public awareness, and improved public perception. The study proposes a framework for selecting national and cross-border CCUS clusters and hubs value chains. The framework is applied to 8 case studies in the Baltic and Mediterranean regions, in total 11 countries involved, and has been developed by the CCUS project. More I will tell that technical and non-technical data were first collected and integrated into a unified GIS project for 8 countries in the Baltic region and 5 countries in the Mediterranean region. And on this map, you can see a location of these scenarios on the map: Baltic 1, Baltic 2 and 3, and Baltic 4, and Mediterranean 1, 2, 3, and Mediterranean 4. Red areas are the storage sites for CO2. To realize the proposed objective, the SWOT analysis approach was selected. SWOT analysis, which stands for strengths, weaknesses, opportunities, and threats, is a strategic planning technique used to assess various factors related to project planning. To quantify the SWOT analysis, we will apply the methodology established by Chang and Huang at the next step of the study. The quantified SWOT analytical method incorporates the principles of multiple attribute decision-making using a multi-layered approach to simplify complex issues. Since we need to analyze both quantitative and qualitative data, a statistical methodology is necessary. In this study, it was suggested that the weights of internal and external factors be treated equally. The weights of key factors will be calculated using the analytical hierarchy process as proposed by Sarti and applied to the SWOT analysis by Chang and Huang. This methodology could be applied at the final steps of the study after clarifying how many parameters, technical and non-technical, could be analyzed together statistically for all the proposed CCUS projects. First, technical and non-technical data for two regions were collected and integrated into GIS. CO2 emission sources, CO2 storage sites, red polygons, emission sources you can see on these two maps by yellow and blue circles. Natura 2000 areas, light green areas on the maps, and available infrastructure, pipelines and ship routes. 8 large CCUS cluster projects were selected, with 4 projects from each studied region for more detailed technical analysis, integration with CO2 use options, and consideration of non-technical parameters. Here you can see the selected parameters: total produced CO2 emissions, number of emission sources and clusters, storage sites, total CO2 storage capacity, total years for storage, distance from emission sources to storage sites. We established internal technical factors and external technical and non-technical factors. Technical data includes layers with large CO2 emission sources, CO2 storage sites, available pipelines infrastructure, CO2 use options, and Natura 2000 areas. Qualitative, non-technical data were collected via literature review as well as experts' input across social, regulatory, political, monitoring, reporting, and verification, and financial issues. Internal technical factors are originally quantitative parameters, each characterized by its units and polarity. Here I didn't show the polarity of the factors. In total, 24 internal technical factors were developed. For the CO2 emissions plans group, the factors are the number of countries, clusters, plants, fossil and bio CO2 emissions, captured CO2 emissions, number of plants, planned CO2 capture, and hydrogen production. For the CO2 storage sites group, the factors are number of storage sites, porosity, permeability of the reservoir rocks, well injectivity, thickness of primary cap rocks, CO2 storage capacity, and storage readiness level. For the infrastructure group, the factors are transport distance maximum and total CO2 emissions per distance unit, number of wells in operation and old abandoned wells, number of planned PCI projects. For the CO2 option group, the factors are number of CO2 use projects in operation or R&D, longevity of CO2 use products by CO2 to be used. External factors are originally the qualitative parameters, both for non-technical and technical aspects. To assign them quantities, we developed for all of them questions with numbers to be answered from 0 to 6 for non-technical parameters and from 1 to 5 for technical. For non-technical aspects, we assign positive polarity, and for the technical external aspects, negative polarity. In total, 5 external technical factors were developed. For the area in and around the storage site group factors, storage site located in the densely populated area, storage site area belonging to landlords, storage site located in the seismic risk area, storage site located in Natura 2000 area or other protected areas, transport routes are going through Natura 2000 area or other protected areas. And 9 non-technical external factors were adopted. For social group, the factors are level of public acceptance, political development, international regulations, London Protocol application. For the national regulation group, the factor is the implementation of EU CCS directive. For the monitoring, reporting and verification group, the factor is monitoring, reporting and verification readiness. For financial group, the factor is governmental financial support for CCUS. And for the readiness of CCUS value chain group, factors are value chain readiness and CCUS in industrial strategy or plan. Here you can see examples of maps of non-technical layers in GIS, national and international CCUS regulations, public acceptance and political development, readiness of CCUS value chain, monitoring, reporting, verification, and accounting readiness, government financial support for CCUS projects. And here, example of non-technical data combined with technical data. International regulations and national CCUS regulations together with CO2 storage sites. Okay, briefly about every cluster project. The first one is the Baltic 1 cluster. Latvia and Lithuania, location of the map you can see here. The Baltic 1 onshore cluster includes 4 of the largest Latvian CO2 emitters and 2 Lithuanian plants located close to the Latvian-Lithuanian border. I can see them here and here. Orlen refinery and Akmenės cement plant owned by Schwenk. This cluster will store annually 3.1 million tons of CO2 from 3 plants, Latvian and Lithuanian Schwenk-owned cement plants, and Orlen refinery. In the onshore Blidene and North Blidene geological structure, Latvian 2 Latvenergo power plants and 1 Riga's Siltumus thermal plant located in the Riga region here will transport about 1 million tons of CO2 in the Dobele storage site in western Latvia using up to 150 kilometers CO2 pipelines. You can see this scenario here. 41% of CO2 emissions in the Baltic 1 cluster are coming from the cement industry. The main advantages of the proposed projects proposed project are the close location of the onshore storage sites, very good reservoir properties of diamond formation sandstones, explained by low temperatures, high CO2 density, and therefore large storage capacity, high storage readiness level, and the readiness of the main industrial stakeholders to develop CCS projects like Schwenk, Latvia, Latvenergo, and Orlen. The main challenges of the proposed project are non-technical, including regulatory and social, considering that the storage site land is owned by local landlords and the CO2 storage ban has not been yet raised. Governmental financial support from Latvia and Lithuania is not yet provided. Baltic 2 cluster, you can see on the European map the location for Germany, Denmark, and Sweden. And the Baltic 2 combined onshore and offshore cluster offers 8 storage sites in Denmark, which have excellent reservoir properties. These sites have thick primary cap rocks and high storage capacity of approximately 1 gigaton of CO2. There are various options for transporting CO2 from 9 emissions clusters located across 3 countries to 8 storage sites, which are situated onshore, nearshore, and offshore. Additionally, CO2 capture and use options are currently under development, and numerous research and demonstration projects related to CCUS are ongoing in Denmark. The supportive CCS policies, regulations, and financial government aid in Denmark, along with the implementation of international regulations in Denmark and Sweden, are significant advantages. The 2 offshore sites are under development by commercial parties. An exploration license has been issued for the onshore Gazum site to Wintershall International and INEOS. 9 emission clusters were identified with 33 individual emission sources in total, resulting in 22.7 million tons annual maximum emissions and captured maximum amount near 20.1 millions of tons. 2 CO2 utilization pathways were explored with this region, converting CO2 into methanol or synthetic jet fuel. The Swedish flagship one e-methanol project, the largest of this kind in Europe, was recently cancelled by Austrian in August 2024, and no potential off-takers have been identified. However, Denmark and Germany still have active CO2 utilization projects. Notably, the power-to-liquid plant in Hamburg, developed by Intertek, will produce about 200 tons of e-fuels to transport and 150 tons of e-waxes for cosmetic, pharmaceutical, and food industries. The main risk for this project involves international regulations for Germany, which has not amended Article 6 of the London Protocol or submitted a provisional application to the International Marine Organization. However, the EU CS directive allows a bilateral agreement between CO2 emitters and storing countries to serve as a legal basis for the export of CO2 for geological storage beneath the seabed. Baltic 3 scenario, you can see here on the map, related to Germany, Denmark, and Sweden, is a cross-border value chain with 5.9 million tons of CO2 emissions produced by 16 plants from Denmark, Sweden, and Germany, and 3 storage sites, Havnso, Stenlille, and Rodby, onshore and nearshore Denmark in Zealand and Lolland. The total average storage capacity is about 224 million tons of CO2. The distance from CO2 clusters to storage sites ranges from 5 to 15 kilometers. Two CO2 emission clusters in Denmark, Copenhagen and northwestern Zealand, produced about 1.9 million tons of CO2 in 2021. The South Sweden cluster produced 1.5 million tons of CO2, and the Rostock cluster produced 2.5 million tons of CO2. The Baltic Sea combined onshore cluster has 3 storage sites available. Exploration licenses have been issued for the onshore Havnso site and the Rodby storage site. The proposed value chain promotes cross-border cooperation for 3 countries, translating potential investments possibilities being studied today by multiple parties. The Copenhagen cluster also shows interesting potential for CCU applications, with a lighthouse project of green fuels for Denmark receiving IPCEI funding for producing CCU fuels from captured CO2 and renewable hydrogen, now unfortunately suspended. The main challenge for this project could be the same as for the Baltic 2 project, connected with international regulations. Baltic 4 cluster, related to Poland. You can see here location. Baltic 4 value chain includes this southern cluster of the northern Poland region, the Kujawa-Masovia cluster. There are 11 selected emitters within the cluster, producing 8.2 million tons of CO2 per year to be captured, stored, or used. Two saline aquifer structures, Konari and Kamionki, located near the 4 emitter subclusters, are proposed as storage sites with a CO2 storage capacity of 381 million tons of CO2, where CO2 can be delivered by 108-kilometer long pipelines connecting the emission clusters and storage sites. Currently, there is no specific information on stakeholder plans for CO2 use among emitters in the value chain. However, Orlen's facilities in Plock and Wrocław produce blue hydrogen and generate relatively pure CO2 stream as byproduct, which can be used for various goods. The advantages are high storage capacity, close location of emitters to storage sites, 2 PCI projects in this cluster. The onshore option is more economic. The challenges are regulatory, social, local landlords who own the storage site land, and no governmental support exists. Among higher readiness value chains are CCUS projects with the CO2 emission sources in Denmark, Sweden, and Germany, and CO2 storage in Denmark, Baltic 2 and Baltic 3 scenarios. The main internal strengths of these two value chains, the high storage capacity associated with very good reservoir properties, the large thickness of primary cap rocks, CO2 capture and use options are under development, many CCS research and demo projects in Denmark. Their main external opportunities are the favorable CCS policies and regulations of financial governmental support in Denmark, where CO2 storage sites are located. Sweden and Denmark have deposited a declaration of provisional application of amendment to Article 6 of the London Protocol. Among the risks for Baltic 2 and Baltic 3 is German international regulations. Germany has not deposited a declaration of provisional application of amendment to Article 6 with the International Marine Organization. This, in addition to a bilateral agreement, is needed before the export of CO2 for offshore storage. The Baltic 1 and Baltic 4 value chains are characterized as less ready due to regulatory risks associated with CO2 storage onshore in Latvia and Poland. Respectively, industrial scale CO2 storage is not permitted in Latvia and Poland. In Poland, CO2 storage is now permitted offshore in the Baltic Sea. However, considering that the Helsinki Convention doesn't permit CO2 storage in the Baltic Sea, it is not possible now to inject CO2 offshore Baltic, and regulations on onshore storage are still being developed. Despite the planned changes in the CCS regulations and other available technical strengths, these regulatory changes in Latvia and Poland may take additional time, and the risk should be seriously considered. Now we will review four Mediterranean cluster projects. Here we can see it all at a glance. Mediterranean 1, 2, 3, and 4. The Mediterranean 1 value chain includes two emission clusters, the Soma cluster and the Izmir Alia cluster in Turkey, along with an offshore storage site in Greece. CO2 emissions from the Soma cluster are transported to Izmir Alia via 120-kilometer pipelines and then shipped to the Prinas storage site by 360 kilometers away. The Mediterranean 1 value chain can enhance energy and environmental cooperation between Turkey and Greece, fostering regional collaboration. Capturing CO2 emissions from industrial areas like Alia and Soma can reduce their climate impact, helping Turkey meet its Paris Agreement commitments and align with the European Green Deal. Additionally, the Prinas Basin has a good capacity for CO2 storage, benefiting the local economy and the regional energy sector. The Mediterranean 1 value chain encounters several challenges, including technical, economic, social, and regulatory issues. A significant challenge is the lack of accessible annual CO2 emission data in Turkey, leading to reliance on IPCC reference approaches for calculation. This may create uncertainties in total emissions. Additionally, the presence of seismic activity in both countries complicates the CO2 storage process. Economically, establishing new infrastructure such as pipelines and ships requires significant investment to ensure feasibility, and the absence of carbon pricing mechanisms makes this even harder. Finally, international regulations pose a major obstacle, as neither Turkey nor Greece is a part of London Protocol, complicating CO2 transportation and storage in offshore formations. The Mediterranean 2 project features 3 emitter clusters and 1 offshore storage site in Spain. The Tarragona cluster has 5 emitters, and Barcelona cluster has 9 emitters, and the Fos-Marseille cluster in France has 18 emitters. The geological storage site for CO2 sequestration is offshore Tarragona in the Ebro Basin, with a capacity exceeding 200 million tons for CO2. Additionally, options for CO2 utilization are being assessed in France and Spain. In this scenario, the CCU facilities are situated near the gathering stations within each cluster. The Mediterranean to CCUS value chain can significantly reduce emissions in the selected clusters. The Fos-Marseille cluster is ahead in development, as the EU has classified it as a project of common interest for a CO2 export terminal. Repsol Exploration is seeking a permit for CO2 storage at the Castellon site, Tara CO2, which would enable offshore CO2 storage in Spain with a capacity of 200 million tons. That is, which is sufficient for 20 years of emissions. However, this may challenge the economic viability of value chain, because it should be traditionally 30 years for reduction. The Mediterranean 3 value chain is localized project in southern France that includes a paper plant and a cement plant near Bucqueur, which together emit 1.17 million tons of CO2 per year. The Del Baon saline aquifer, located 30 kilometers away, will store up to 34 million tons of CO2. An onshore pipeline will link the emitters to the storage site. The storage capacity is tailored to manage emissions from 2 neighboring plants, providing a local solution for nearly 30 years. Transport infrastructure investments would be minimal, as distance would not exceed 40 kilometers. The Del Baon aquifer, located at depths of 200 meters, allows for CO2 storage in the gaseous phase, which limits capacity and raises leakage concerns despite a thick seal. Additionally, nearby protected areas, such as Natura 2000 sites and the bird protection zones, could complicate the development of CO2 storage and transportation in the region. The Mediterranean 4 case involves on-land pipelines in southern Italy, extending from Priolo Gargolo to Brindisi. The Brandanica storage facility is near Taranto. Additionally, ship transport from France and Greece is proposed with harbor in Brindisi. The main advantages of Mediterranean 4 include a high capacity CO2 storage site with effective caprock and nearby emitters hubs that can utilize pipelines from industrial clusters. Cross-border connections from Greece and France can be integrated, and there are good CO2 utilization options in a sector like cement, iron, and steel refineries and chemicals. However, challenges exist, including seismic risk in Italy and new regulations that permit experimental storage only in depleted offshore oil and gas fields with ongoing injection in Ravenna. Additionally, densely populated areas and Natura 2000 sites within the storage site complicate onshore storage option. In the Mediterranean region, Mediterranean 2, 3, and 4 value chains, which include correspondingly emission sources and storage sites in Spain, France, and Italy, are assessed as ready, while Mediterranean 1, including CO2 emissions from Turkey and the CO2 regulation and emissions from Turkey and CO2 storage in Greece as less ready, considering the regulatory risks. There is a lack of CCS regulations and CO2 capture and transport infrastructures in Turkey. Turkey and Greece are not contracting parties to the London Protocol and are therefore not bound by requirements for cross-border CO2 transport. The study closes with an overview of readiness and recommendations for advancing ready and less ready cases toward CCUS implementation. Some projects in both regions have also risks for the storage site area. Italy is planning to implement an amendment and a provisional application to Article 6. However, the technical parameters of the storage site in France, in Mediterranean 3, are not qualified for the needed requirements. Technical risks for the area around the storage site in Italy and Greece, seismic risks should be checked for the storage site area. Most countries have risks connected with the location of Natura 2000 areas close to storage sites or intersect with the storage sites. And conclusions, integrated quantitative analysis can be conducted for both offshore and onshore CCUS projects. However, these projects must adhere to different regulatory frameworks, international, regional, and national regulations for offshore projects and bilateral national regulations for onshore projects. Despite these differences, it is possible to perform a unified quantitative analysis for all the projects, both onshore and offshore, by utilizing common internal technical factors and streamline the list of external technical and non-technical parameters. One area with significant uncertainties involves the CO2 utilization options. These uncertainties arises from the lack of established regulations for bio-CO2 emissions, the early stages of project piloting and demonstration, and uncertain market conditions for CO2-based products. So we thank for support European Union Horizon Europe project and the UK Research and Innovation Fund. And thank you for your attention. If you have any questions, please. Welcome. Or yes, you will have opportunity to ask me at the end of the presentation. Next presentation. Thank you.
Hello. So I'll be presenting the second part of this webinar, and I'm aiming for a smooth transition now. So my name is Leandro, and I work in Rumble. I hope you can see my screen and hear me well now. So
all good.
Yeah, thank you. So Kazbulat has presented an important part of the CCUS project, which was the definition of different value chains. And now, out of these projects that were defined, we propose ourselves to select potential projects of common interest according to the U system of classification. So this is what I will dwell a bit about for the next minutes, and it's a short presentation. I hope you'll have the chance later to see the full report once it's released. But let's start first with some definitions. So the EU defines projects of common interest and projects of mutual interest. Both of them are define important projects that are cross-border, that are related to energy or decarbonization, that promote sustainability, that promote for market integration, competitiveness, energy security. But what's the main difference? The PCIs, the projects of common interest, are applicable for projects that involve member states of the EU, and PMIs extend further to neighboring countries as well. So in this project, we are mainly focusing on the PCIs. And actually, the EU provides a transparency platform, so a map where you can explore which PCIs and PMIs are active right now and which stage are they on, if they're on feasibility, construction, operation. and you can filter them out for which ones are related to the CCUS industry. So focusing on the PCIs, then we need to so we can select out of these value chains that Kasbulat presented applicable projects for an EU PCI. We need to define what are the requirements, and these are actually very specific and detailed in the TENE regulation, so the Trans-European Energy Infrastructure Regulation. This is a regulation that defines what type of projects within the energy and decarbonization areas would be applicable for PCI. It defines 11 priority corridors, so basically geographic areas where projects could lay down their equipment, and they are defined by electricity, offshore grids, hydrogen and electrolyzer grids. But besides that, the regulation also defines 3 priority or thematic areas, and one of them is related to CO2 networks. So it's basically the development of, and I'll quote, development of infrastructure for transport and storage of carbon dioxide between member states and with neighboring third countries if it's a PMI, of carbon dioxide capture and storage captured from industrial installations for the purpose of permanent geological storage and utilization for synthetic fuels, leading to permanent neutralization of carbon dioxide. So this is the most generic definition that you'll find at the TNE regarding CCUS related projects that could be eligible for PCI. The regulation actually goes a little bit for defining types of equipment that would be applicable in this context. Pipelines. So we need to remember that we're talking about a cross-border project. So pipelines, for example, are a very good example of an infrastructure that usually crosses a wide longitudinal area. So it would there is a big advantage on crossing it through different countries. But also fixed facilities are included in the TNE, like liquefaction facilities, buffer storages, any type of equipment that converts CO2 to different phases for further transportation on ship, on barges, on trucks. It also includes the geological infrastructure, the injection on the geological storage infrastructure, and it even includes any equipment that allows the system to operate correctly, securely, efficiently. For example, monitoring systems. So all of this could be included in the PCI project. The projects must involve at least 2 member states. That's very important. And the TNE also defines a couple of values that are important to ensure that we are ticking off the box, like the security of supply, the market competitiveness and market integration. Very important, the sustainability EU goals. So these are very important values that we need to bring into our project to build a case to apply for a PCI. The PCIs are then once we apply for them, they are selected biannually. They are this process is steered by different groups, so delegates that are chosen from the European Commission, the Agency for Cooperation of Energy Regulators, and national regulatory authorities, which analyze the project from different perspectives throughout the different disciplines. And the main benefits of achieving EU PCI status is firstly related to an accelerated permit granting process. So this allows for a streamlined permitting process, improve regulatory conditions that promote transparency, trust from the investor side, and facilitate the development of the project. The EU also promises that the PCIs allow for lower administrative costs by streamlining the environmental assessment processes. and it increases also the stakeholder engagement. So it requires the involvement of many different stakeholders, and this brings visibility to the project. And last but not least, it also makes the project eligible for the Connecting Europe facility, which is basically a financial support that could ensure that this project goes to the next phases and help it become successful. So and this applies to feasibility studies and construction. So now we have defined the ground rules for defining a PCI. Now let me show you. So based on the projects that Casvolat has defined, we have selected different potential PCIs. So we are not proposing them to the EU Commission now, that we are not stating that these are for sure would be for sure be accepted as a PCI, but these are proposals from our project. They are there could be more. So Casvolat has presented 8 different value chains. We are presenting here only 4 value chains. We could present more. We could subdivide the projects that Casvolat has presented into different parts or divisions that could be more easily achieve PCI status. So the idea of these 4 projects is that they define different aspects of multiple projects, and the idea is that they will try to process CO2 from 9 million tons per year from 7 million tons per year to close to 20. So let's dive deep a little bit into details of each of them. The first one is related to the Baltic 2 project that Casvolat has presented. And if you recall, the Baltic 2 project is a large project that includes 22.6 or 7 million tons of emissions per year. This project is a pipeline and shipping network that combines 3 different countries, Sweden, Denmark, and Germany. So what we are doing for this proposal for PCI is just dividing the project and looking only at the connection between Germany and Denmark. So we are proposing a pipeline that connects both countries, and only this pipeline would unlock close to 40% of the emissions accounted in the Baltic 2 project. So it's a very important piece of infrastructure that would be very important for the German industry. It allows for the transport of 7.4 million tons of CO2 per year, and the distance is around 200 kilometers. So after defining in a very high level the project that we would like to propose, we made something like a benefit analysis, a very high level benefit analysis, where we analyze the contribution to market integration, and in this case we have 9 emitters located in Germany that could benefit from this infrastructure and proceed with their respective industries operations. We are also promoting or encouraging the development of CCUS related industries with 8 potential storage sites being connected in Denmark, and also CCU capacity estimated at around 1.7 million tons per year in Denmark. The main contribution to sustainability in this case is the reduction, the decarbonization and emissions reduction. In this case, 7.4 million tons is around 2.7% of the EU Industrial Carbon Management Strategy goal by 2040. So this could also be an important project to achieve that. And regarding the cross-border impact, we analyzed the potential regulatory frictions that could happen between the different member states. In this case, both Denmark and Germany are contracting parties to the London Protocol, so that could help easing the frictions between both countries. So these 3 topics of the benefit analysis are important for the application for a UPCI. There are some missing, like an economic analysis, which we haven't done here, but we tried to make a high-level case for this project here. If we move to the next one, it's this project is again a pipeline. Instead of a single pipeline, is a pipeline network. It's actually an extension of an existing PCI, the ECO2 CEE PCI, which is basically a connection to a port in Gdansk for shipping of CO2 to storage sites in the North Sea. So the original PCI was sized to around 3 million tons of CO2 per year processed. This extension would allow for 9 million tons per year, and it consists of a pipeline network that goes over Lithuania, Poland, of 932 kilometers. The project can also extend a little bit further. We have analyzed the potential of Czech Republic also being included in this network. So in terms of contribution to market integration, we have analyzed 20 different emitters. We have an important harbor facility located in Gdansk and potential storage sites in the North Sea. We also promote CO2 transportation by railway systems, in this case to Czechia. Regarding sustainability, we are here aiming to reduce, to decarbonize up to 9 million tons of CO2 per year. And also, when talking about sustainability, and remember, we're building a case for applying to EU PCI, it's also a good idea or a good point to talk about the environmental impact of these structures. I mean, we are talking about pipelines which are permanent longitudinal infrastructure that affect the terrains that they are installed in. So if we take that into consideration and find sustainable solutions, sustainable routing of the pipelines, for example, this could also help make a good case. We haven't gone that far in this project, but it might be important to have that in mind. And finally, regarding the cross-border impact, the three emitter countries are not contracting parties of the London Protocol, oppositely to the potential storage sites in Denmark, in Norway, UK, and so on. So this could be a friction between when allocated responsibilities of the emissions between the different countries that must be taken with care between the different commercial parties negotiating. The third PCI that we proposed is related to the Mediterranean 4 project that Kasbulat had presented. So it's divided in two parts. So we have a pipeline system in South Italy that collects CO2 from multiple emitters there until a geological storage site. But we also added the possibility of shipping of CO2, mainly from Greece, but also potential with the potential to extend to France as well. So this allows for the process of 3 million tons of CO2 per year, and distances from emitters to storage site vary between the local ones, 50 kilometers, to further ones located at 500 kilometers, for example. So this integrates potential 24 different emitters, and it includes here we would need to include different stakeholders as ports, harbors, and promote the creation of storage site industries that could inject the CO2 in Italy. We are promoting here the reduction of 3 million tons of CO2 per year. This is about 1% of the industrial carbon management strategy for the 2040 objective. And regarding the cross-border impact, Italy and France are contracting partners of the London Protocol, but Greece is not. So this is also a potential friction point that we must ensure in the application phase that we have it planned and it's clear who is responsible or who owns the responsibility for the different stages of the value chain. And the final PCI, we defined this one at a more later stage of the report. So it's a bit it's not as completed as the three ones before in the report, but you can it's related to the Mediterranean 2 project that Casbolat had presented. It has a capacity of 9.8 million tons of CO2 per year, and it's basically a pipeline and harbor infrastructure located in Tarragona. So the harbor located in Tarragona that you can see here in a map, and the pipeline that connects Barcelona, that connects Tarragona to the offshore geological site. Here we are encouraging the capture of potentially 32 emitters in the 3 clusters that we have defined, and CO2 we are integrating pipelines, harbors, ships, and 1 potential storage site. So we are this is how we are promoting a new industry and ensuring that the existing 32 emitters can remain competitive in their areas. And regarding the contribution to sustainability, this is 9.8 million tons of CO2 captured per year. It's close to 3.5% of the industrial carbon management strategy objective by 2040. So to finalize, I would like just to give you 4 highlights so that we concluded in this report regarding of what would be the key parameters when applying for a UPCI. And the first one is related to technical preparation. So this is one of the key aspects that are assessed on a UPCI application. It's important that the developers display their experience, to understand that or define the project at a level of definition that is realistic and pragmatic. And it's important to show the the track record and potential historical projects that could also make a good case for achieving a successful PCI. And sometimes this requires the partnership with other institutions, because these are large projects. These involve different disciplines that often cannot be found in one organization. So the partnership aspect of PCI projects is actually very important and should be taken seriously. The second point is related to the stakeholders. It's a key factor, actually. In the report that we developed this table that I kind of call it a yellow page or a yellow book of potential contacts for potential stakeholders in the regions that of the 4 projects that I presented. This will ensure that the project has visibility, but also has endorsement from different parties, and this will be very important to make the project successful. We also need to check the level of maturity of the project. If it needs to have a level of definition where multiple scenarios have been screened. So this one is a strong project that could be taken forward. The PCI projects are not necessarily projects that will be successful. So they will go through feasibility studies, they will go through FEED studies, and challenges may arise. But a minimum screening should be done beforehand. And finally, on the financial aspect, the PCI unlocks a lot of potential investment for the PCI, but the project developers must ensure that they can raise the necessary funds to finance the project as well, or at least from the different sources or different investors. They could stump the budget necessary to develop this project, and this should be clear in a PCI application. So these are the 4 key points that we have achieved. And I end my presentation here. So I'm looking forward for your questions now. Thank you, everyone, and thank you also for our sponsors for this project.
Thank you, Leandro, and thank you, Casbolat, for both your presentations. We have about 5 minutes for questions. I'll take a moment while everybody decides if they want to submit a text question. I'll take a moment to enable microphones and cameras for attendees just now. Microphones and cameras are enabled just now. Please raise your hand using the hand raising feature on Teams if you'd like to ask a question. I'll take a moment to mention one of the questions that they came in chat about the slides. So yeah, the recording is available and obviously the slides will be within them, but if you prefer a PDF version of the slides will be posted on the website along with the recording. So I'll endeavor to have that within 24 hours or so on the website. Have we got any questions? Please raise your hand on Teams or please feel free to send a text question. Something coming in through the chat. Thanks for presentations, very interesting. Thank you very much. Always see if we have any additional questions or any hands being raised. I'll take the opportunity to promote the 5th webinar for the project, which has been published on the website and it's taking place in about 3 weeks. So I'll take a moment to put that in the chat, and I invite you all to please register for that. We do have a hand up. Michael, please unmute your microphone and ask your question.
Yes, hi, this is Michał from Bellona Europa. We've been following the project with great interest. So thanks for the presentations. I was intrigued by the mention with regard to PCIs and the different partnerships. In your experience or to your knowledge, did you see any partnerships involving NGOs in any of the CO2 network PCIs or PMIs?
Yes, and actually, it's a quite important. We actually have defined the potential PCI partnerships in terms of regulatory authorities, NGOs included, financial institutions, and project developers and partners. And we've developed this kind of yellow book in our report related to this. So NGOs are definitely an important stakeholder to keep in track on, to not only in terms of hearing their opinions, and especially related to local communities and NGOs related to local communities, having them engaged in the project from an early stage is quite important to make the project successful and avoid opposition when we don't have those opinions integrated into our project, or those objections also sometimes. So definitely, yes, I completely agree with your statement.
Thanks. I can just confirm that we as Bellona have been approached several times with requests to send a letter of support. So if we deem a project to be truly climate beneficial, we are always happy to support such projects.
Yeah. Thank you.
Thank you, Michał. We got time for maybe 1 or 2 more questions. If I see most attendees are still around, but if there are any additional questions, please raise your hand. There's something coming in the Q&A pane. Bear with me a second. Could you please give a rough idea of a time frame for PCI project acceptation and the FID step?
It can depend. It depends also on the size of the project itself. So I don't have these numbers with me, but I mean, we are analyzing projects from 50 kilometers of pipelines to 900 in our suggested PCIs. So there is a very wide difference between the time to mature the project and the time for it to be reviewed, the time to also to acquire the stakeholder engagement that we need. So yeah, I don't have an exact number, but it's a quite important aspect.
Thank you, Leandro. Maybe we have time for one final question. Oh, okay. So a reminder anyway that slides will be available. Both Caswell and Leandro have included their email addresses, so you can contact them directly if you have any questions that come up just after the webinar. But all that remains for me to say is thank you very much to both our speakers today. Thank you everyone for joining us today during this webinar. We hope we see you in 3 weeks' time for webinar 5 that looks at a very detailed development plans for the 2 selected CCUS value chains for the Baltic and Mediterranean Sea. So it's a good follow-up from today's presentations, and I hope to see you all following the project on our social media accounts and staying on top. And please, we invite you also to sign up to our newsletter on the website. So with all that, thank you very much once again, and we hope to see you next time.
Thank you.
so
Have a nice
much.
day.
Thank you.
Thank
Bye-bye.
you, everyone.
Thank you.